Alright, so the other announcement is I have to announce a date for the next midterm sometime soon, so you can all plan for it. Sometime around mid-November. Okay. Week of 10th of November is what I'm thinking, because that will be 2 or 3 weeks between that midterm and the final exam. So I don't want to delay too much. I didn't want to have it next week because they just finished the lab, so I want you to recover a little bit from it. Okay, the week after next week or something, or later part of it. So let's get started here. Just a quick recap of what we were talking about last time. So if you remember, we have gone through quite a few different memory management schemes by now. We started with contiguous memory allocation, we looked at paging, we looked at this technique called segmentation and segmented paging. Okay? And then we said we need to somehow relax the requirement that the entire process be resident in main memory at all times, and that the process cannot be greater than the size of RAM. Okay? So the main insight is we are going to use the 90-10 rule, which says the process only uses a small fraction of its memory pages at any given time. So that basically leads you to the observation that you don't need to keep all of the pages of the process in memory. Only the process of pages that are active, which we will define to be the working set. Okay, in a class or two, we will talk about the working set. So the working set is the set of pages that the process is actively using at any given instant. And the observation is the working set of the process is much smaller than the total pages it owns at any given time. So our insight is you don't need to keep the entire process in memory. Keep only some small fraction of its pages. Keep the rest on disk. Okay, so essentially, the disk is where you are going to keep all of the loaded process. We have a special portion of the disk which we will call swap space. Okay, this is where we are going to keep all of the pages, and pages of a process are going to be fetched into memory as and when the process needs it. Okay, the pages that are not used can stay on disk. Okay, in this manner, you can have processes that are greater than the size of RAM. So now the size of RAM is no longer limiting. You only need to allocate a small portion of memory for that process. It doesn't matter what the size of the process is anymore. Okay? Also, you can have a lot more processes than would fit in RAM at any given time. So essentially, you have done away with the limitation that you have a certain amount of RAM. Whether you have 2 GB, 4 GB, 8 GB, doesn't matter. You can still start a lot more processes than your RAM would normally allow you to, and you not use this scheme. Okay? So this scheme is referred to as demand paging. It's also referred to as virtual memory. Okay? Based approaches where the disk is now a form of virtual memory. Your main memory, which is physical memory, and virtual memory is really the disk, which is pretending to be RAM. Okay. So I already mentioned some of these things. So we are going to come up with this technique now. Design is technical. This lab, which is going to be demand paging. We are going to use memory essentially as a cache. Okay? The disk is where everything is stored. Memory is a cache, so it stores a subset of the pages of the process. Everything else is on disk. We are going to have a page table which has additional information now. The page table now has to track not just which frame in memory a page is resident. Pages can now be resident on disk. And so the page table can point to some element of this, some element is RAM, and so on. So page table is still tracking everything. But well, it's going to track whether a page is in disk or in memory. If it's in memory, it's going to tell you where in memory it's stored. Okay. So whenever a page is brought from disk, the OS is going to put an entry in the page table, and there is a valid bit that it's going to use. Mark it 1. 1 says that the page is in memory. 0 says that that page is on disk. So if it's 1, then you look at the entry in the page table. That's going to point you to the frame like before. Okay, but you have to first look at the valid bit to see where the page is. Okay. So we already talked about the 90-10 rule, which is that 90% of the time a process accesses a small, approximately 10% of its pages. Those pages we will refer to as the working set. And typically for the process to perform well, you just need to allocate it enough memory so that its working set is resident in RAM. The working set itself cannot be stored in RAM. The process is going to page fault a lot. It's going to keep accessing pages that are on disk. You're going to fetch a page from disk. That process is called a page fault. It's very slow, okay, because disk is much slower than RAM. So you can't keep going to disk very frequently, it's going to impact the performance of your system. Okay, so this is the picture to keep in mind. You have a page table. Okay, so the page table, some pages of the process are in main memory, so those pointers are going to point to main. If the valid bit is not set, the page table will indicate to the OS that that page is on disk, and this is your disk. Okay, so these are actually pages of processes that are stored on disk. So as I said, you will have all the process pages always on disk. Some fraction of them will also be in RAM. Any questions on this? We will now talk about how to make all this work. So just a quick recap from last time. Okay, so now we look at several different issues that come up. Okay, the first question is when to load a page into memory. Okay, when the process starts up, we'll assume that all the pages are on disk. So the question is when do you load it? There are several options. Okay, you can load pages at process start time. Okay, but that's going to, if you load all the pages at start time, you don't need virtual memory. All the process pages are in memory, main memory. Okay, so then you don't need the disk, so that doesn't give you any advantage. Okay. You can also do something called request paging, where the process can indicate to the OS what are the next set of pages it may need. Okay. In this case, the OS can fetch those pages for the process before the process actually starts accessing them. So then, whenever you need a new set of pages, you just tell the OS, this is what I need. The OS fetches it for you, and the process executes, and everything it needs is always in memory. Okay. It sounds like a good idea, but then it requires the process to be able to predict, or the OS needs to predict on behalf of the process what pages the process may need and fetch it into memory. Okay, so this is going to be a form of pre-fetching, and it requires knowledge of what is going to happen in the future in terms of what pages a process is going to access. Okay, that is something you may typically not have access to. You cannot always predict the future. It requires you to figure out what is this process going to execute, which part of the code is it going to execute in the future. You may not know. That piece of code will depend on user input. The user may click on something that may cause the application to do something. You don't know what the user is going to do. Okay, so request paging is not always going to be feasible, but it is an approach. In scenarios where the process can predict or the OS can predict on behalf of the process, the OS can fetch the pages from disk into memory before the process starts accessing them. And then you don't need to worry about page faults and so on. Okay? So that's the second approach. The third one, which is the middle approach there, is called overlays. Okay? It's actually an old approach that's not used anymore. In overlays, it is the job of the application programmer to explicitly fetch pages and put pages from memory to disk and fetch pages from disk to memory. Okay? Back in the old days when virtual memory was not supported at the OS level, okay, you were basically restricted by schemes like normal pages. The entire process had to be stored in RAM. You could write programs where you as an application program manages the memory. Okay, you can basically allocate different chunks of memory and write explicit code that reads in that piece of memory and writes those old pieces back to disk. Okay? So this is a form of demand paging, but done by the application programmer for his or her process. Okay? This technique is called overlays. It was something that was used in old operating systems that did not support paging. Okay? Now you don't need to do this because the OS will do this for you. Okay? Think about it. If you have to write an application where you have to decide, okay, now I'm accessing this code, it's accessing these data structures. I don't need those other data structures. So let me write that out to disk. When I need them at a later time, I'm going to read that back. So you have to write code in your application to do explicit memory management. It makes process programs much more complicated. But that's what you have to do if you have no other choice. OS doesn't do it for you. And you need to have processes that are bigger than what your RAM can accommodate. You have to basically write your application as overlays. Overlay simply means that you can have one part of the process overlaid on some other part which has been saved to disk. Okay, so if you have, but if you look at operating systems like DOS or Windows 3.1, very old operating system, this is how programmers had to write code. They did not have access to demand page. Okay? Questions on this? Can you repeat which mechanism is used? Is that your question? Okay, so we are going to go to the next mechanism, which is demand paging, which is going to address all of these limitations. So the problem with the first one is the process has to be resident in RAM. Okay, that's going to be a limitation. There is no problem with the second overlay approach, other than it's now application become more complex because the programmer has to write more code. The third one requires you to predict the future. That may or may not always be possible. Okay, so they each have some advantages but some limitations as well. Okay, so fourth approach is going to be demand paging, which is you fetch pages on demand. Okay, so what the OS does is OS says that it's not going to do anything until the process actually requests a page that is not in memory. Okay, let the process execute. Whenever it executes an instruction that accesses a memory address, say in a page that's on disk, we are going to have what's called a page fault. Page fault says that the process touched a page that was not resident in RAM. So at that point, the OS is going to go off. It's going to suspend execution of the process. It's going to go off and try to fetch that page. Okay? Eventually, it's going to read the page from disk into memory. Okay? At that point, you can resume execution of the process. You restart that instruction that caused the page fault. Okay? This is called demand paging. Okay? There is no need to guess anymore. Okay? You do whatever the application asks you to do. It's touching some pages. If some of those pages are not in memory, you fetch them. Okay? And to do that, you may have to decide which pages to evict. Because when you bring something into memory, you may have to throw something out of memory if there isn't any unused frames in memory. Okay? So you are going to go through this process which says load a page every time it's accessed, okay, and you have a page fault. So page fault is the interrupt that will occur whenever an instruction touches a memory page where the valid bit in the page table is set to false. Let's say the page is on disk. At that point, you are going to throw an interrupt, service the interrupt, bring the page and restart the process. Okay. So that is what most operating systems will do today. Okay. So they are going to use demand paging, the most general purpose operating system. That support virtual memory will employ some form of demand paging where they will let the process behavior dictate when pages are brought into memory. Okay. So, and then pre-paging is a form of request paging where you may have to guess in advance, and if you guess right, you will actually not stall the process. Because if you see maybe the application is sitting in a loop and it's accessing the same set of pages, if you cannot store them all, you have to see what pattern the pages are being accessed in, and then page bring the pages in just before the process accesses it. Again, requires you, this is again a form of pre-fetching. It requires you to guess. If you guess right, then the process is going to have fewer page faults. If you guess wrong, you may actually make things worse because you brought pages into memory that the process doesn't need, and in doing so, you have evicted some pages that the process may actually need. Okay, so it will actually not work if you start guessing wrong. It will make things worse. But if you guess right, you can make the performance better. A page fault is going to stall an application process. Okay? There are lots of page faults in the system. This is a scenario called thrashing. Yeah, I don't know if any of you has noticed, but sometimes if your memory on your system gets over-committed, you start lots of processes that are all memory intensive, you will see that the disk will start spinning. The application performance will slow down. The system is very slow, seems to almost have hung. The disk is constantly churning. What's actually happening is all the processes are paging. Okay? They're constantly bringing pages from disk to memory. In doing so, you evict something else, and then some other process needs it soon after. Then you bring that page in. And there's a lot of IO every process gets slowed down. Okay? That's a scenario where the system performance is going to be very slow. You don't want to get there. Okay? So you want to ensure that you have as few page faults as possible to ensure good performance. Questions on this? Questions? So now let's talk about a few other issues of how to go about implementing. So these are all the steps you have to perform during demand paging. Okay? So we'll make some assumptions. Okay? The first assumption is a copy of the entire process will always be stored on disk. draw some pictures here. So let's call this the process A. So let's say it has some pages, 4 pages. Page table for the process. Okay, this is the valid bit. Okay. And then we're going to have RAM and a disk. So we say disk has 2 parts. This is the file system. And this is the part that is going to swap space. Okay, this is the picture to keep in mind. There's main memory, there is disk. A disk has a small part that's reserved as swap space that you typically will not even see if they're invisible to users. And there's the file system that you store your normal files. Okay, that's a process. Okay, that's a page table. So we'll call this your page 1, 2, 3, 4. Okay, so what we're assuming is first, a copy of all of these pages will always be on swap space. Okay? Some subset of those pages will also be in memory. Okay, so let's say page 1 is here. Page 2 is here. Okay, so 2 of those pages are in memory. The first question is, why should we keep pages that are in memory also on disk? Isn't that duplicating pages? So you see page 1 is both in memory and on disk. Yes.
Because if at some point you stop using that process, you still want to have a copy of the heap that gets there.
Okay. Yes.
So you don't have to waste time copying it back to the disk.
Okay. So the point being made is, if you have to throw out a page to bring in a new page, if it's already on disk, you don't have to waste time copying it back. Okay? That is indeed true, and it's only true if the page was not modified. You remember that if the process actually writes to the page is going to be different. Now, your newer version of the page here and an old version of the page there. If a page has been modified and it is being evicted, you do have to write it to disk because the copy of disk is older. Okay? But if the page was not modified, let's say it's a page that contains source code which typically won't change, then you can simply overwrite this frame with some new page. You don't have to write that back to disk. So you're always going to keep a copy on disk. Okay? That's the reason we have that. Okay? There's a valid bit in the page table that's going to store or say whether the page is in memory. So anytime you have a page in memory, that entry valid bit is 1 and the pointer will point to the page. The valid bit is 0, that indicates to you that the page is on disk. Okay. Now, if you access a process A executes an instruction that accesses page 3, or let's not say page 3, but let's say page 2. Okay. What will happen is when you access page 2, you will try to convert that logical address to a physical address. You will go look at the page table and find that the entry there is 0. That indicates to you the page is not in RAM. This is going to trigger a page fault. Okay? And then that's an interrupt. Okay? So when an interrupt occurs, all of these steps have to actually take place. So the first thing you are going to do is say, I need to bring this page in. Where should I put it in memory? Okay, where in RAM does it go? So you may decide that if there are no, so here we have unused pages, so you can just put it there and that's fine. But if all of those pages were in use, you have to decide something to evict. Okay? So that algorithm that decides where to, which page goes out in order to make room for a new page that's coming in is called page replacement. We are going to look at 3 policies to do page replacement today. Okay? So let's say you now decided to throw out some page. Okay? If you do that, you have to go to the page table and then mark its entry 0, saying that page is now gone. Okay, it's gone, so it's now on disk, it's been thrown out of memory. Okay, so you invalidate the old page in the page table, then you start reading, so you issue a read request to the page 2, in this case that was accessed, you try to say read it in, so you send that request to the disk, that's I/O, so it will take a while for the page to be read in. Eventually the read operation will complete, and that page will be brought into memory. Yeah, you will put it wherever you have decided to put it, which is at the location of the old page. So while all of this is happening, okay, you are going to context switch and execute some other process, because this, so essentially a page fault is equivalent to the process triggering I/O. Even though the process is not actually doing I/O, all it did was it executed an instruction that touched a page that was not in memory. Okay, but as a result of that, the OS has to go read the page. So implicitly, a process has done I/O. So while you are doing I/O, some other process will run. So while a page fault is being serviced, several other processes may run. You context switch to other processes, and other processes may run in the meantime. Eventually, once your page comes into memory, the interrupt will be serviced. Okay, you will update the page table. Okay, so page 2 has been brought into memory, so you are going to say that's 1. Then you put it here. Okay. Now the page is in memory, and then you are going to resume execution of the process, and by that what it means is that you will re-execute the instruction that caused the page fault. Okay, that instruction couldn't execute because it touched the memory page that was not in memory. You will restart that instruction and then the process is continued. Okay? So all of these steps have to take place in order to service the page. So next question.
So does the page table have to store an address for both the disk and for memory?
Okay, so that's a good question. The question is, does the page table have to store an address for where the page is on disk? So notice that I did not, when the page was 0 here, I did not say that. Okay, so you do have to track where the pages are on disk, where the pages are in memory. Okay, so you can certainly track that. But however, you don't need to necessarily track that using a page table. You can use any other data structure to do that. Okay? So page tables are typically only used to track where the pages are in memory. Okay? The reason you don't need to track that where the pages are on disk is because disk is relatively large. You can afford to use things like contiguous memory allocation on disk. Okay, because you have a lot more disk than you have RAM, so you can store the process contiguously. So all you need to store is the starting address of the process. And then if you say, give me the 10th page, you know where the 10th page is on disk. Because you know the starting address is stored contiguously. If you don't store the pages contiguously on disk, indeed you will have to have some data structure, like the page table, which tells you where all of the pages are on disk. Okay, so you can do one of those two things. Either you can just store the process contiguously on disk, and then you just need to know the start address, and the 10th page is some offset from that start address. You don't need page tables in that case.
Will you store the start address?
You will have to store the start address, but it's stored in the PCB, not in the page table. So you have the process control block, which is going to store it.
When the process is going to I/O, as you said, what is preventing that page that just got loaded from being overwritten by the other process that is currently running?
Okay, that's a good question. The question is, when you are loading a new page, what prevents some other process from not overwriting the page? Right? So that's a good question. So this goes back to how the OS is going to allocate memory for processes. Okay, so it's the OS's job to allocate memory for different processes. So there are many ways you can do that. I will talk about that in the next class. So one thing you can do is allocate a certain amount of memory to each process. Say this process gets 20 pages, some other process gets 15 pages. So in that case, the process can only evict its own page. When you bring something in, you only evict your own page. Okay? This is called per process memory management. Okay? So if you have per process memory management, if some other process falls in the meantime, they won't override your page. They can only override that process's page alone. Okay? And there's also something called global memory management, where all the pages are on one large pool. So one process can cause some other process's page to get evicted. This can cause problems where if you start paging in a lot, some other processes' pages are gone, when it runs, its performance degrades. So you have to do that carefully, because you can actually hurt some other processes' performance. Or a malicious application can just start doing mallocs. You just sit in a group and do a lot of mallocs, you get a lot of memory, everybody else's pages are gone to this. Okay, so if you do have processes like that, you can get impacted. Now, having said that, the specific case you mentioned, you asked about what happened, because when you are bringing in a new page, OS is going to lock the page, saying this page is in use right now, it's being brought in, so you can't evict that way. some other page may get evicted if you're using global memory management. Okay? Yes.
Can you explain number 7?
Can you explain number 7? Continue forwarding process. So basically what's happening is that you took an interrupt, eventually your page came back in, so you continue the process that was faulting. Okay? Faulting process is the process that generated the page fault. Okay, that's the process that is done over this.
What's the current?
Current process is the process that's running because you have page faulted, that's IO, some other process starts running. Right? So that's the process. So when your page has been brought into memory, something else is running on the CPU. Okay? And you are basically saying that process was evicted from the CPU because it caused a page fault. So rather than continuing that process, if that page has been brought back, I'm going to resume execution. Okay? Because it should at least get back on the CPU and start executing from where it left off.
That's one more.
That's going to be context. Okay, so that's implementation of demand paging. Okay, so now we have this swap space that I was mentioning. Okay, which is this region of disk that is going to keep all of your pages that are not in memory. Okay, so as I said, you have to keep a few things in mind. Whenever you evict a page, you have to check whether the page was modified. If the page was modified, you can't simply throw it out and overwrite it. You have to save a copy to disk, because the copy on disk is older. Okay, it's assumed that when you modify a page, you don't start writing it out immediately because that's expensive. Okay, right? The IOs are expensive, so you just keep a copy in memory. It's modified. If at some point that page is selected for replacement or eviction, at that point you'll go write it out. Okay? And if not, then you say that the copy in memory is the same as the copy on disk, so I can simply overwrite that page and I can fetch it again at a later time. I already have what I need on disk. So you have to distinguish between these two scenarios. Okay? So that's one thing. The other thing is you can perform some additional optimizations where the process doesn't actually need to store its pages on the code segment on disk. So remember I said process can have multiple segments. You can have a code segment, you can have a stack segment, a heap segment, and so on. Okay? So if you have a code segment, you may not need to store it. Okay? That's an optimization. Okay? So you will only store pages on the stack and the heap here. Okay? The code segment you don't need to store. Okay? So why is that? So what happens if you evict a code page and want to bring it back again? Where does it come from?
Which is from the file system.
Okay, so one suggestion is comes from the file system. People understand why it comes from the file system. So a process is a program you loaded from memory. It's machine code that was compiled and is sitting on memory, sitting on disk. So if you brought it in, there's already a copy of that file on your disk. Okay, so you will actually have some, let's say you're running Chrome. Okay, your Chrome .exe or Chrome whatever executable is also on your file system. Okay? So when you bring it in, some of these pages are those code pages. So if you put that back, then you have two copies, one in swap space, one in the file system. So one optimization you can perform is pages of your code segment of a process you do not need to keep in swap space. You can simply bring them from the from the file system when you need to. Okay, is that clear? So what might happen if you are actually running a process and then you delete its file from this? Then what will you do?
It would keep running until the page was invalidated.
Okay, it would keep running until the page was invalidated, and then what will happen after that? You can actually try this experiment. You run a process, start some program, okay? Delete the file from disk. See what happens. Okay, so depends on the OS what the behavior is. Okay, so the straightforward scenario is you delete a file. If there's an active process that was swapping from the file because it did not, as an optimization, keep the code pages on swap space, the process will simply crash at some point. Because it will have a page fault, it will try to fetch the page from disk, and it relied on the page being in the file system, but you went and deleted that file because there's nothing to swap in from. Okay? And then the process will simply crash. Okay? Now some operating systems, what they will do is they will actually try to address this specific case. So whenever there is a process swapping from a file, okay, the OS will keep track of it. So if the user actually deletes the file, it will delete the file itself, but not delete the blocks of the file. The blocks of the file will still be on disk. They will be hidden from the user. You can't see the file. The file is gone, but the space hasn't been reclaimed. The space is still allocated. The blocks are still there, so you can still page from it. Okay? And only after that process is terminated do you actually release the disk space. Okay? That's an optimization. If you have an OS that does that, then your process will not crash. Okay? So you can try it on Windows and Linux or Mac and see what happens. Depends on the flavor. Okay? Some OSs will not do this and the process will do it. So it is an optimization to say you don't need to keep code pages on swap space. You can just bring them from the file system when you need to. You are relying on the fact that users don't go and start deleting files off. That's a rare case, and in that case, you let the process crash. In the common case, in the uncommon case, you do something smarter about what delete actually means. Okay, you don't have delete the data. You only remove the file. Yes.
Okay, so if we can just load files from the file system, why do we need swap space?
If you can load the file from the file system, why do you need swap space? Okay. So the question is, if the data is already in the file system, why do you need swap space? So if you look at a process, okay, as I said, we have multiple segments. You have the code segment, you have the stack, you have the heap. Okay. What is in the code segment is what is actually your exe files. Okay. The stack and the heap are running state of a process. That's not in the file system. Okay, that's what the process is doing. So those pages have to be stored on swap space. So it's all segments other than the code segment. Any other questions here? Okay, so now we'll talk a little bit about performance of demand paging. So we should ask the question, we made certain things better, which is we now no longer are limited by RAM. Process can be bigger than RAM. Okay, a lot more processes whose size store exceeds RAM by a significant amount. But in doing so, we are now bringing pages from disk. Okay? That's going to be a performance slowdown. We want to analyze what the performance slowdown is. Okay, so before I present the analysis, we'll try to see why in reality you won't actually see a significant performance slowdown. The performance slowdown will be slight. And this is because processes exhibit what is called locality of reference. Okay? And there are two kinds of locality of reference, what's called temporal locality and spatial locality. Okay? Temporal locality simply says if a process accesses page I, okay, it is very likely it will access page I again in the near future. Okay? Temporal locality is locality in time. You access a page, you are very likely to access the same page in the near future. Okay? It should be clear why temporal locality exists. Let's say you are sequentially executing a program. Okay? You execute an instruction, let's say the 10th instruction. It's in a certain page. Okay? If you are sequentially executing the process, you may then execute the 11th instruction. That's likely to be in the same page. Okay? So you access the same page again, and then you access another instruction. Until you have a branch, a loop or a branch, or you executed all the instructions on a page, you are going to access the same page over and over again. Or if you are accessing variable I in some part of snippet of your code, that snippet may access that variable again in the near future. Okay? Access to that variable I again brings you back to the same page where I is stored in the stack. Okay? So all of these observations give rise to locality, temporal locality, which is a process accesses a memory item or a page, it will access it again in the near future. Okay, what spatial locality is locality in space, okay, which essentially says if a process accesses page I, it's very likely that now it's going to access a neighboring page. Okay, that there is locality in space, either the same page or a neighboring page. Next. And that basically comes from, you have a data structure that says an array, you're accessing the array may straddle 2 pages. Since you're accessing the array in your code, you may access some element of the array that's in one page and then another element that's in the next page. Because you may be performing some operations on the array. So these kinds of access patterns give rise to spatial locality. Okay? So what this is telling you is accesses to memory is not random. Okay? It doesn't mean if you access, let's say, page 3, okay, the next page you access is completely random. Okay? Typically, it's going to be determined based on the spatial or temporal locality, which means you access a certain page, it's very likely the next time you access, the next instruction also accesses that page. Okay? Or if you access a certain page, the next instruction may access a neighboring page. Okay? Both of which basically say that access patterns are not random, okay, because of the behavior of processes. Okay? This is what is basically going to give us the 90-10 rule, which is basically saying that at any given time you're accessing a small set of pages that arises directly from temporal and spatial locality. Okay, because you're either accessing the same page or some neighboring set of pages. So now those are the pages you're acting on, not some other random page typically. Okay, over a period of time, the working set may shift. You may access some other set of pages, but at any given time, you have a working set. Okay? And now, what does all this have to do with our performance analysis? What they should tell you is because accesses are not random, okay, demand paging is not going to have very bad performance. Okay? If you store a small subset of pages of the process in memory and the rest are stored on disk, performance is still likely to be okay because not every instruction is going to start faulting. Okay? If every instruction starts creating a page fault because you access some other random page that you don't have in memory, the performance will be terrible. Okay, but your spatial and temporal locality helping you. It says you bring in some set of pages, the process will work on those pages for some period of time. So for some period of time, you will not see any page faults at all. All the pages the process needs are already in RAM. Okay, is that clear? So this is just a qualitative argument saying that paging is not going to result in bad performance. Okay? If on the other hand you had processes that exhibited completely random behavior in terms of page accesses, paging is actually going to not work for that process. It's going to have a lot of page faults. Because no matter what page you bring in or what substrate you bring in, next time it accesses something completely different. Get another page fault. Okay, then your performance will not be good. You'll see that the process slows down quite a bit. Okay? So that's the qualitative argument as to why paging is going to work for us. Now we do this somewhat more quantitatively, which is essentially this equation here. It's not a difficult concept. So basically we'll assume that T is the probability that any instruction triggers a page fault. Okay? So probability that there is no page fault is then 1 minus T. Okay? So then the question is, if there is no page fault, what is the cost of memory access by an instruction? And if there is a page fault, what's the cost of a memory access? So let's take the simpler case. Let's assume there's a page fault. Okay, what's the time to execute that instruction? So what is happening during a page fault?
Just load the page from disk.
If you have a page fault, you're going to load the page from disk. Okay? So that instruction execution time is going to include at least one disk I/O. Because it's trying to execute the instruction, it immediately faults, you go off, try to bring the page from disk, you resume execution at some other point in time. It should be clear that disk access time is much, much slower than the time to execute an instruction, orders of magnitude slower. Yes? So if you have a page fault, okay, which is with probability P, the access time or the instruction execution time or whatever, memory access time, anyway you look at it, is going to be the disk access time, which we will call T. At least the time to do one I/O from disk. Okay. So now let's take the case that you do not have a page fault. Okay, what is the cost of executing an instruction? The time to execute an instruction. Okay, let's for simplicity assume that the instruction accesses has something that causes one memory access. where you go to the Twitter. Okay. So there are two ways to answer this question. One is to you just say, okay, if you do either you access if the page is in memory, in which case the cost of executing the instruction is simply the time to access memory, and we are ignoring the cost to actually execute the instruction on the CPU, and we call that M. Or the pages, you have a page fault, so you go to disk, and that's going to dominate the latency. Okay, so it's 1 minus P times M plus P times D. Now, that's an approximation because as was just pointed out, you also have to actually include the time to look up the TLB, the time to look up the page table, all of those we have simply ignored. The last time when we were analyzing the performance of paging, if you remember, you said depending on the probability of a TLB miss, you had TLB plus M plus 1 minus T of TLB times. If you remember, this is the expression we wrote last time. It said depending on how the TLB performs, you have a TLB hit or a TLB miss. For the TLB hit, which is the common case, the time to access memory is simply M. If you have a TLB miss, you are going to go to the page table which is in memory and then access the memory. So you have two memory instructions. Okay? This was our expression. So technically this should be this. Okay? But we are ignoring the TLB miss here. We are simply putting this expression here and then we are ignoring the TLB also. But technically, if you want to write the real expression, it's going to be the probability of a page fault times the time to access this plus there's no page fault, and if there's no page fault, this is the time it takes you to access memory, okay, which is the cost of executing that instruction. And all of that we have simply simplified as M in this case. Okay, ignoring all of this and just looking at that. Not a common case. Is that clear? Yes? Okay, so that's clear. Then you should ask the question. Here are some actual numbers. Okay, we now assume. So let's take this expression just for simplicity. Ignore all of this additional stuff, which is the same as this expression here. Okay, 1 minus P times the memory access time plus probability of a page fault times the page fault time, which is time to access disk. Okay? So now we are going to give some real numbers. It says time to access memory is 200 nanoseconds. Okay, this is still slow, and today's memory is much faster than this, but let's say it's 200 nanoseconds. Page fault time is 25 milliseconds. Okay? That's the time to do an I/O. Again, this is somewhat old disk. Today's disk will do it in 5 milliseconds or 1 millisecond. But that's okay. So we'll assume memory access time 200 nanoseconds, page fault time takes 25 milliseconds. So it's an effective time to execute an instruction. The average time to execute an instruction or average access time is 1 minus P times 200, just 200 nanoseconds, plug it in there, plus P times 25 million, which is 25 million nanoseconds of the page fault time. Okay. So you should understand that page fault takes 25 million nanoseconds, memory access takes 200 nanoseconds. So it's several orders of magnitude slower. So page faults are not at all desirable because you could have executed several 100,000 instructions in that time it takes you to execute that one instruction because it faulted. Okay, so this is just going to give you some idea of what happens in either of these two cases. Now let's ask the question, so that is your effective memory access time. If you want only a 10% slowdown in your performance because of page fault, then what should the probability of the page fault be? Okay, is that clear? So that's the question, the last bullet there. So depending on the probability of a page fault, you can basically get different levels of slowdown. So lots of page fault, you'll have significant slowdown. So we are asking the question, if you want to limit the slowdown to be only 10%, 10% of a case where you have a process always in memory. Okay, so there are no page faults at all, that's the baseline. And from there we say you can afford a 10% slowdown. Then the question is, what should that probability be? Yes.
So you like 1 in 1,000.
So you can just do the math there. Okay, so 10% slowdown says effective memory access time should be 220 nanoseconds. So if you have no slowdown, every memory instruction will take 200 nanoseconds. Because if the process is completely in memory, there's never a page fault. Okay, so each memory access is going to take 200 nanoseconds. Effectively, you want now this expression to be equal to 10% slowdown, so this side is going to 220. Okay, so you can just plug that in, which is 220 equal to 1 minus p times 200 plus p times 25 to 10 to the power 6. So if you do this, you'll see this becomes 20. So you can just do this equation. Basically, what you're going to get as P is effectively 10 to the power minus 6. It's not exactly, but that's what it's going to be. So the probability of a page fault should be 1 in approximately 1 million instructions. That's what it's saying. So if you want only a 10% slowdown, every millionth instruction that the process executes can afford a page fault. Any more than that, your performance will be much, much slow. So now you have to think about what does this have to do with. So the locality of reference should be such that once you bring the working set in memory, you need to execute approximately 1 million instructions before the process touches a page that's not in memory. If you do not get that, then you are going to have much more worse performance. So those are the kinds of numbers that have to work for you or the OS for all of this scheme to work well. Otherwise, users will perceive a significant slowdown. If every 10,000 instruction you have a page fault, that's going to be big trouble. Because significantly more slower performance than just a 10% slowdown. You may get 60, 70% slowdown. Okay? So now you should understand that for paging to actually work well in practice, page faults have to be very rare. That's really the takeaway. Okay, so now we'll just look at some more additional details, which is we sort of ignored all the TLD stuff during a page fault, but that's not quite what's happening. You have a page table, you have some things on disk, some things in memory, there's a page table, there's a TLB, all of these data structures have to be updated. So I think the way it's going to now work is the TLB will also have a valid bit that's going to tell you whether the page is in memory or on disk. Okay, so there will be a valid bit there. If that bit is 1, then you know that the page table entry is cached and the memory page is in memory. That bit is a 0, then you have to actually go to the page table to see if the page is in memory or on disk. Okay, so we'll have to keep multiple valid bits. There's a valid bit in the page table, okay, that tells you whether the page is in memory or disk. There is also a valid bit in the TLB that you will have to maintain. That's going to also tell you this information. So if you have a valid bit, it says the page is in memory. So on a TLB hit, you're done. It's a fast start. If you have a TLB miss, then you check the page is in memory. So you're going to go to the page table, which is itself in memory. If it's in memory, then you are done. You bring it into the TLB. Oh, that's only a TLB entry miss, which is updated there. The page is already in memory. If the page is not in memory, then you have a page fault. Okay, so then you are going to do all of this. You validate the page table entry, you perform the page table operations from all of those things in the previous slide. Then the pages are going to arrive in memory. It's going to be, you put an entry in the page table. You're also going to, put the entry in the page table. You also put an entry in the TLB, update the TLB, and then you restart the TLB process. Okay. So a lot more bookkeeping. Okay. Multiple data structures have to be maintained. There's a TLB, there's a page table, there's a swap space. All of these have to be maintained during a page fault for any instruction that executes from memory. So you'll see that the complexity of our memory management scheme has grown significantly. We started with continuous allocation, and the only thing you needed were base and limit registers. Now we ended up with demand paging, where your processes are in multiple places. There could be in the file system, it could be in swap space, it could be in RAM, page table entries could be in TLB, it could be in main memory. So you have to deal with all of that complexity. So what that should tell you is modern operating systems have fairly sophisticated memory management schemes that have to manage all of these data structures to make it all work for the user. Okay? Okay, so the last part is from a user standpoint, none of this matters. All of this is being done by the operating system. It is completely transparent. By user, you mean actual processes. To you, it's completely transparent. You may not even know what there is paging and all of that, but even processes don't know. All that the process is doing is it's executing its instructions, and instructions have a logical address. The fact that there is paging going on, let alone demand paging, is unknown to the process. You're simply doing the translation, and there's the hardware and the OS is doing everything else for the process. Because the process doesn't have to do anything extra in order to take advantage of all of this. Okay, it just simply executes instructions like it did previously. Okay, so all of this is done by the OS with some hardware support. Okay, so there's one small issue we'll talk about, and we'll move on to page replacement. And that's the issue of making sure the page fault is transparent. Okay, what does that mean? So, if you remember, what I said was page faults occur when you're in the midst of executing an instruction and the instruction accesses a memory address in a page that's missing from memory, so a disk. Okay? So, this has happened actually literally in the middle of executing the instruction. Maybe you said, this is a move instruction where you move a memory address from into a register. Okay? So you are in the process of accessing the memory address to bring that variable into a register, and you trigger a page fault. So in most cases, what happens is you suspend execution of that instruction. Okay, although it was in the midst of execution, you're going to suspend, service the page fault, and restart, and everything is fine. Okay? But there are some instructions where actually that is not the right thing. You will have to actually look at what the instruction did in order to restart. And here is an example of such an instruction. So this says move A R10 plus. So what is it? This is a move instruction. And this says increment the value in register 10 and move that value into variable A, which is stored somewhere in memory. Okay, so this is a simple instruction. Many CPUs will have instructions like this where you can increment a register and move it to a memory address. Okay? So now you think about how this instruction executes. Okay? So it starts executing, it says go to register 10 increment. Okay? Whatever integer is stored there is incremented. Then you try to move that register into address A. At that point you are going to try to convert address A into a physical address, and then you find there's a page fault. And you could say, I suspend execution of this process, you go off, you do something else, page comes into memory and you restart. When you restart, you can't start from half the instruction, you have to start from the beginning of the instruction. And that's something you should have be clear. You can't say I executed half the instruction last time and you will execute the next half. Now, it's all or nothing, you execute always instructions from the start. So you restart and say increment register 10 and move it to A. So you'll go back to register 10 and increment. But keep in mind that the first time you try to execute it, it already incremented that value. So if you do this again, you incremented it twice. And now you have a problem because you basically had an instruction that has a side effect that actually changed something during its execution. And if you simply suspend it and do nothing, then you are going to basically have some problems. Okay? So what that also says is your hardware, when there's a page fault, needs to be smart enough to figure out what instruction was actually executing when that page fault was triggered, and did that instruction do something that you have to undo, because later on you are going to restart the instruction, is going to do the same thing again. Okay? So in this case, your hardware will have to decrement R10 and restart at a later point in time. Okay? All that adds complexity. It can be done, there's nothing that prevents you from doing it, but for every instruction that could potentially trigger a page fault, you have to think about what could it have done that I want to undo, so that when you restart it again, you haven't done that thing twice. Okay? So these are all additional subtleties that you typically don't think about, and you say, okay, let's access memory I, go bring the page restart instruction. It's not as simple as that. There are all these funky instructions that are going to cause some trouble for you. Okay? But this one is actually easy to undo. Okay? You simply go decrement alt. There are other instructions that are much more difficult to handle, and here is an example. Okay? This is basically a copy instruction. Okay? You have this instruction that say copy a region of memory from one location to another. So what this is saying, with this instruction, it gives start address and end address. That's the source address and end address. And say take this region of memory and copy it here. And those two regions are actually overlapping, as you will see. Okay? And that region are just two addresses. They can span multiple pages. So you can just say, take this start address, take this end address, take this entire chunk of RAM and copy it somewhere else. Give another destination start and a destination end. Okay. Now let's say that region had 10 pages. Okay. So you start executing that instruction. You take the first page, you copy. Okay. And let's say both those pages are actually in RAM, so there's nothing wrong with that. You take the second page, then you copy it again. Okay. Now you try to copy the third page, let's say there's a page fault. Okay. So now how do you undo this? Instruction was already overwritten some pages. Because whatever you copied, the old page where you copied it is gone. You didn't save it. You can't undo it and say, okay, I'm going to do a reverse of a copy. There is no such thing. When you copy something, whatever was in that page has been overwritten. Okay. If you have incremented a register, you can decrement. You say take a page and copy it somewhere else, and now you can't uncopy it and bring back whatever was in that destination back. Okay. All those bits are gone. Over. Is that clear what the problem is? So these kinds of instructions you can't even undo. Once you start executing, whatever you have done is not going to be undone. Okay? So the only way around this is before you even start executing it, the only way you can actually ensure that you're going to execute it is you look at all the pages that this instruction is going to touch. Make sure they're actually all in RAM, and none of them will be a page fault, and only then you will start executing. Because if you're in the midst of executing and you hit a page fault, there is no going back. You can't undo anything or overwritten. Okay? So for these kinds of instructions, it's even more complicated to handle page faults because you can't undo any side effects. Okay? Is that clear? Any questions on this? So these are all additional implementation details. When you try to service page faults, you have to ensure that when you restart the executing instruction, it doesn't do something that is going to be problematic. So you want the execution to actually have the intended effect. Okay, so that's all I have about demand paging. Now we will talk about this issue of page replacement that I alluded to earlier. So this is the problem of when you have a page fault and you are bringing a new page in, you are going to throw some page out. Typically, if you don't have any unused pages, you have to evict a page in order to make room for a new page. Then the question is which page to evict. Yeah, it depends. So there are many different policies or algorithms to do this. They are all sort of referred to collectively as page replacement algorithms. Okay. And you will see the reason this matters is why do I care? Why not just pick some random page and throw it out? And you will see that depending on what choices you make of which page to evict, that actually has an impact on the page fault rate. Okay. The number of page faults you may encounter may be dramatically higher or lower depending on what choices you make on what to evict. In particular, if you make the worst decision to make is you evict a page that the next instruction accesses. Okay, so the next instruction, so you create another page fault in servicing a page fault. That's the worst of all scenarios. Okay, so you have to make this decision well, and we are going to look at 3 different techniques that will do this. Okay. The first one is first come first serve or FIFO. Then we are going to look at one called min, which is an optimal technique. Okay. And then we are going to look at a technique called LRU, or least recently used, which is a common technique. Okay. That's the one that most operating systems are going to use. Okay. But before I even start talking about them, is it clear why you need to think about page replacement, or what it is before why you need to think about it? So this is simply a problem of there was a page fault, you're trying to bring a new page in, there isn't room in RAM, there's no unused pages, so you have to edit the page. Okay? Which one are you going to pick? Okay. So, as it turns out, random, which we are not going to talk about, I just said it may have performed badly, that's not the case. In reality, making a random decision, you just toss a coin and say pick a page. Okay? Works quite well, surprisingly well. Although most operating systems don't use random, but that policy, if you actually compare it with some of the other techniques, it actually doesn't do that bad. So it's not a bad approach, although I said that it should be that something random, but we'll not talk about random. Okay, so let's start talking about first come first. So what does first come first serve do? Or FIFO do? Okay, FIFO says throw the oldest page out. New page comes in, so you keep a timestamp on each of the pages. Okay? So whenever you bring a page in, you put a timestamp. You take the current time and say this page was brought in at this time. So every page you have as a timestamp that says when that page was brought in. Okay? So now if you have a page fault and you need to bring a new page, you throw the oldest one out. That's first come first or FIFO. That's the order in which you brought them in. Okay, so you look at all the timestamps, pick the oldest timestamp, that's the oldest page. That's the page that was brought in first. That's the one that's going to be evicted. Okay, so that's FIFO. Is that clear? So, min is also called an optimal approach, actually says that throw the page out that is likely to be accessed farthest in the future. Okay, so now think about this. So let's assume that for now, just assume that the process knows what it's going to do in the future. You know which pages it's going to access and in what order. So now if you want to throw a page out, you look at, here are the pages I have. When is page 1 going to be accessed next? You look at the time in the future is going to be accessed. When you say when is page 2 going to be accessed, look at what time in the future is going to be accessed. So among all the pages, you throw one out that's going to be accessed the farthest in the future. Okay? That policy is referred to as the main policy. Okay? And it should be immediately clear that whenever you say, I know what's going to happen in the future, that's not a practical approach. You don't know the future. Okay? But assuming you knew the future, what min will do is you throw the page farthest in the future. Okay? And the reason this policy, which is not at all practical to implement, is interesting, is that it's an optimal policy. No other policy can do better in terms of page fault rate. Okay? If you look at how many page faults min gives you, there's no policy that's going to give you any less than that. It always has to be at least that or more. Okay? So in other words, this policy is going to minimize the number of page faults. If you could know the future, you could have a policy that gives you the absolute lowest page fault that any system can give. Okay, that's min, and we look at this in more detail. Okay. And the last one is called LRU, or least recently used. Okay. What least recently used policy does is when you bring in a page, you look at when each page was accessed last. So now you have timestamps on when the page was accessed, which is different from the timestamp when the page was fetched. And they're two different things. Okay? In case of FIFO, the timestamp tells you when the page was brought in. In case of LRU, say when was the page used last? You might have brought it in 10 minutes back. That's okay. If 10 instructions ago you access the page, this timestamp is going to be whatever that timestamp was when the instruction executed. So that's the timestamp of last use, not the timestamp when you brought it in. Okay? So what LRU will do is it will throw out the least recently used. So you look at all the pages and say which page was accessed, was the least recently accessed page, and you throw that page. Okay, this is referred to as LRU. Is that clear? So now we'll actually look at an exercise and try to work our way through actual examples of how FIFO works and LRU works and how min works. So we'll take a very simple memory. Okay, your memory is 3 frames, frame 1, frame 2, frame 3. The memory can only hold 3 pages. Okay? We'll assume that there is a process that has 4 pages, A, B, C, and D. Okay? 4-page process, 3-page memory. You can't hold the entire process in memory clearly. Process is bigger than memory. At most, you can store 3 pages of that process. Okay? And then the third information that's given to you is this is over the course of the execution of the process. These are the pages it has accessed and in that order. So there's it executes an instruction that accesses A, and executes an instruction that accesses B, and then C and so on. So you have that access tree. Okay, that's called a reference tree. That is basically you actually look at the execution of the process, and that's the order in which its instructions are accessing its memory. Okay. So now the question is given a system with 3 frames, a process with 4 pages, and that access pattern. If you are using FIFO replacement, what would be the contents of memory and how many page faults you would get? Okay, that's clear what I just said. So we work through it. We don't have answers yet. We don't have the pages of the board. So we have frame 1, frame 2, frame 3. ABC. That's our access pattern. Okay. So this is how the instructions are executing, and that's the memory access pattern. So first instruction accesses A. Okay, so you have to ask, is that a page fault or not a page fault? Okay, the memory is empty, there's nothing in memory. Okay, so that's obviously a page fault. So you are going to fetch A. Okay, you can put it in any of the unused frames. So we'll put a check saying that was a page fault. Okay. Next, you access B, also page fault. B is not yet in memory. So you bring B in, A can stay there, you have space for B, so put it in the second frame. Okay. We're going to access C, okay, page fault. Okay. So you're going to bring C in, there's still room to hold another page, so you're going to put it in the third frame. Okay. At this point, memory has filled up. Any subsequent page faults actually mean you have to evict something. Yeah, so far you didn't have to evict anything. Okay. Then you access A. Okay. A is already in RAM, not a page fault. Okay. So no page fault here. Okay. Memory content don't change. Okay. Then you access B. B is also in memory, not a page fault. Okay. So there's nothing to do. The instruction executes without faulting. Okay. Then you access D. Okay. When it says D in memory, it's not. We have A, B, and C in memory, these 3 pages, so that's a page fault. Okay. So now this is where our page replacement is going to kick in. Now to throw out a page to make room for D. Okay. So which page are we going to throw out? Okay. FIFO says bring the page that was brought in first. Okay, that's A. So each of these pages will actually have a timestamp. Here we can see the order in which they brought it in. The OS, the way it's going to work is it's going to put a timestamp. This time is going to put here this time. And so you look at the timestamp, you look at for the oldest timestamp and evict the page. Either way, you will evict A. Okay, so you have D, B, C. Okay. Now you access A next. Okay, you just evicted A. So you are out of luck here. I'm going to have another page fault. Okay, what do you want to evict? B. Okay, you have to evict B. Okay. You ask which of between D, B, and C, which one was brought in first? B was brought in here, C was brought in here at this point in time, and D was brought in here. Okay, so if you go by order in which they were brought in, this is the oldest page we have among the 3. Okay, so you are going to throw out B. Okay, so D, B, C. Okay, then you access B. Not a page fault, B is in memory. Okay. Then you access B. Okay, that's a page fault. Okay. So you look at when was D brought in, when was A brought in, when was C brought in. A was brought in here, B was brought in here, and C was brought in here. Okay. So C is the oldest page. Yes? So this is a page fault, so you basically okay. So now we have access C. It's going to be another page fault. We just selected it. Okay, so now we are in another page fault. So which of these will be having? Okay, so D. Okay, because we just look backwards and say which is the oldest page. B came in at this point in time. A came in here and D came in here. So D is the oldest page. So this is B. And then B is over here, not a page fault. Okay, so then we just count how many page faults you have. So 3 of them here, 4, 5, 6, 7. Okay, so you have 5 4, you are going to get 7. Okay? So we are going to now do min and then I'm going to stop. Same access pattern. It's just different page replacement policy. Okay, so first 3 accesses page 1. Start with empty memory. Okay. Page 1, page 1, page 1. Okay. And you access A is in RAM, no page fault. Access B is in RAM, no page fault. Okay. Then you are going to access D. Okay, that's a page fault. Okay, now we are doing min. So the question is what will be added? C. Okay, so people say C, which is indeed right. So what you are going to do is you are going to actually look in the future. Okay. So what's the page that's going to be accessed furthest in the future? A is accessed 1 instruction from now. Okay. B is accessed 3 instructions from now. C is accessed 4 instructions from now. So you will have it C. Okay? That's what min says. You look into the future and throw out the page that will be accessed farthest in the future. Here we know the future because it was given to you. Otherwise you couldn't do this. Okay? So we will basically say that's a page fault. And then what you are going to do is throw C out. Okay? Yes?
What would you do if D was the farthest away? Again,
What
just
would you
take the
do?
data and not put in memory?
No, D still needs to come in because there's an instruction that needs it. So you still have to bring D in. You are only looking at the pages that are resident in memory and saying which of those are the farthest in the future. D hasn't even been brought in, so it's not even in running for eviction yet. Okay, you can only evict one of these 3. Okay? Alright. So now because we did this, A is here, not a page fault. B is here, not a page fault. B is here, not a page fault. So you will wait all the way to C, and that's our next page fault. Okay. So now you can evict one of these 3, okay, and then the only thing we know is B is going to be accessed next. So that's the one you will not throw out. You can throw out either of the other 2. Okay, and that's going to be a page fault. So let's say you throw out A. Okay, so we have C, B, D, and then this is the next page fault. So now you see that the number of page faults has reduced to 5 from 7. Okay, 5 4 8 7, opt is 5. And this is the best you can do. There's no other policy that you can do better than this. Okay, that's just an assertion. I didn't do anything. I just showed you an example. Okay. And the reason it's good is you are dealing the page faults as much as you can into the future. Okay, because you're throwing the page that was accessed for this in the future. So the intuition is by doing that, you delay page faults as much as possible. That reduces the overall number of pages. Okay, that's really the intuition as to why this is happening. Okay. So this is an LRU example. I'm going to skip over that. We'll come back next time and do it. Okay, remember, as I said in the beginning of class, next 2 classes are actually guest lectures. So we are going to resume a week from Thursday. Okay, the lectures. There will be a guest lecture on cloud computing Thursday, guest lecture on Linux kernels Monday or Tuesday. Okay. So let's stop here today.